Now we want to start taking a look at angle of twist. And if you remember, we've talked about angle of twist a little bit earlier, and we said that it was the Greek letter phi, capital Phi, and what that is I have a shaft, and I ground one side of it, and I start twisting the other side. If I'm looking at that, if I look at this right on the end here, what do I have? Here's my circle. If I drew a line on it, as I twist it, I'm going to see that line move, and that's our angle of twist, showing us how much the shaft is spinning, basically. Now, a lot of times, we really want to know what the angle of twist is, as opposed to the shear angle, because the angle of twist is a little bit more useful for us. Now, obviously, our big thing is always going to be, hey, what is the shear stress, because that's where things are going to break. But a lot of times, you're going to know how this guy is twisting as we're going along. So let's take a look at this. Now, if we recall, we said that our maximum shear stress is going to be Tc over J, where T is the internal torque, because we're always looking at internals. C is the distance from the neutral axis to the outside surface. In this case, it's our radius. And J is our polar moment of inertia. Now, we do have an equation where we had used angle of twist before, and that was in our shear angle equation, which is going to be CL times phi. So now let's take a look at things in the context of Hooke's law for shearing strain. So what does Hooke's law tell me? Shear stress is G times phi. So everything that we're going to do right now is predicated on that we are in the linear elastic region. Because if we go outside the linear elastic region, if we start plastically deforming it, these equations will no longer work. So this is also, we can say that the maximum shear stress is equal to G times the maximum shear angle. Because your maximum stress is going to happen at your maximum shear angle, your maximum deformation. So let me just rewrite that into shear angle max is going to be what? It's going to be T max divided by G. So what I want to do is I'm going to take this definition here. Oh, that's not the highlighter I was looking for. We're going to take this definition of T max there, and we're going to plug it in right there. And so what I've got is a very big pen. There we go. So all of that is going to be Tc over J, and we've still got times 1 over G. Now what I want to do is I'm going to take this definition for shear max, I'm going to plug that in. So I'm going to say, well, that's also equal to CL over phi. Now, obviously, some of the stuff will cancel out and whatnot, but I just want to jam it together, but I'm going to rewrite it for C. Now, as I do that, my C's will cancel out. Sorry, I want to rewrite it for phi. My C's will cancel out, and what that's going to leave me with is TL over JG is going to equal the angle of twist. And so this is the way that we can calculate out how much it's going to be twisting as we apply a load. Now, and actually this is how they calculate out G for your property tables, is in the elastic region, they plot a line of angle of twist versus torque, and they have a straight line that's got a slope of length divided by JG, and they use this to find what the modulus of rigidity of the material is. Now, this is very similar to all of our stuff that we did with deformation of rods. In fact, it kind of, if you look at it, the deformation is PL over AE. The equations even look similar, not the same. So, but we need to remember is the angle of twist is the sum of all these TL over JGs. So we can have multiple internal torques put on, and then we can find out the twist of everything and add them back together. But once again, just like with the deformation, every time the torque changes, the polar moment of inertia changes, or the material changes, that's when we would use a new equation.